Welcome to CEE222 Week 10 Recitation. So let's start with this first problem 6.5.2. The question asks us what is the difference between the alternate depth and the initial sequence depth. So for the alternate depth, that's number 1, is the depth that has the same specific energy. So if you remember that we have a plot look like this in the textbook, here is the depth and the axis is the energy. So the alternate depth is that these 2 points that has the same specific energy. Okay, so similarly for the initial sequence that is the depth before and after the hydraulic jump. So for example, we have a hydraulic jump look like this. And here is the data for the channel. So this depth is the initial depth. And here is the sequence depth. Okay, so that is the alternate depth and the initial and sequence depths. Let me number this 2, number this 1. Okay. Now let's move on to the next question, 6.5.3. So the question says we have the hydraulic jump occurring in a 5 feet wide rectangular channel. So let's draw the diagram for that first. This is the data. And we have a hydraulic jump. And the initial and sequence depth are 0.66 feet and 3 feet respectively, and we want to determine the energy loss, which are denoted as the delta E, and also the Froude number in the channel prior to the jump, so which is the Froude number at this region. Okay, so for delta E, the difference, the energy lost, we can use the equation 6.2 to calculate from the textbook to calculate the delta E. So the equation 6.2 shows that the delta E is equal to, this is Y2 and this is Y1. Y2 minus Y1 to the power of 3 divided by 4 times Y1 times Y2. Okay, and we know the Y1 and Y2, so we can calculate the energy difference. The energy lost. So 3 minus 0.66 to the power of 3 divided by 4 times 0.66 times 3. And we can get the answer is equal to 1.62 feet. And I encourage you to read the textbook to see how this formula is derived. And so here is your reference. Go to see the textbook and find the equation 6.2, and you can see the derivation for this equation. Okay, so for the second part of this question, we want to find the Froude number, the first section in this channel, which is before the hydraulic jump. And to calculate that, we know the Frog numbers equation is this: velocity divided by the square root of g times y. Okay, so in this case, because we only focus on the first section, so this is velocity on that section divided by g times y1. So we know g is equal to 32.2, and we know y1, which is equal to 0.66. So the only things that we don't know is v2. So we want to find out this v2. And usually, when we're trying to find the velocity in a channel, we use the equation, the flow rate of the unit width divided by y. Okay, so if we continue from our previous section, let me write it in more detail. So in the previous homework, we calculated velocity by the flow rate divided by the area, but this channel is a rectangular channel. So what we usually express in this type of question, we express the flow rate per unit width. So that means we divide by the width b for both a and q, and we can rewrite that into this small q, a lowercase q, and y, because area is y. Area is y times b for rectangular channel. So if you divide by the b, you cancel this out, so the area becomes just equal to y. Okay. So the next question is that, okay, we know this y1 is equal to 0.66. We want to calculate this q1. To do that, we can use equation again. You can find it in the textbook for this equation 6.16, that we have this q squared divided by g will equal to y1 times y2 y1 plus y2 divided by 2. Okay, we have this relationship. Again, the textbook show you a detailed derivation for this equation, so I encourage you to read the textbook. But here we're going to just apply this equation to solve this q, because we know the y1 and we know y2 and we know g, so we can calculate this q. So you just plug in the y1 is 0.66, y2 is 3 feet, g is 32.2, and you type out using the calculator, then we can get that the flow rate per unit width is equal to 10.8 cubic feet per second feet. Okay, so now we know the q, we can plug it back to this equation, so we know that the velocity is equal to 16.4 feet per second. Okay, so similarly this y1 is 0.66. Okay, so we get all the values that that are required for the Frog number, which is here. So I write down here again. So we just plugged in the value. Sorry, a typo. This is V1. So V1 equal to 16.4 divided by square root of G is equal to 32.2 and Y1 is 0.66 feet. Then we can get that the Froude number prior to the hydraulic jump is equal to 3.56. Okay. And this number is greater than 1. So we conclude that this is a supercritical flow. Okay, and there's an alternative equation that you can use to calculate this Froude number. And I just write down here for your reference, and you can also find this equation in the textbook as well. So the alternative equation that you can apply for this problem is this one. Okay, so for this equation, it's fairly simple because you just need to plug in this y1 and y2, then you can calculate the Froude number. And if you do that, you will get the answer equal the Froude number equal to 3.55. And you can get, and it's still larger than 1, so you still have the conclusion that this is supercritical. Okay, so here are just the different equation that you can apply to solve what's asked by this problem. Okay. And again, I really encourage you to read the textbook to see how these equations are derived. Now, let's move on to next question. So in this question, 6.5.5, we want to construct the specific energy and the specific force curves for 5 feet wide rectangular concrete channel that carries 40 cubic feet per second of flow. And the question also asks us to use the water depths from 0.5 to 3 feet. Okay, so let's first write down the information. We have the channel width equal to 5 feet. Sorry. Okay, and carry the flow rate equal to 40 CFAs. So we can also calculate the flow rate per unit width equal to 8. And we want the water depth changing from 0.5 to 3 feet. And we want to plot the specific energy curve as well as the specific force curve. Okay. So for this question, we will need to apply the equation 6.8 and 6.19 from the textbook for this specific energy and the specific force. Okay, let's write down the specific energy equation first. First is the velocity term plus, then plus y, the water depth. And for the specific force, we have the equation F plus rho QV, and this will equal to gamma divided by 2 times y1 square plus rho qv. Okay. Then we can apply those equations to different depths. So here is it. I show the calculation in this table, and I'm going to explain how we calculate the number in this table. So the first column is the water depth, because we want to calculate the value for E and FAs with different water depths from 0.5 to 3 feet. So here is 0.5 to 3 feet with the interval of 0.5 feet. Then, because this is a square channel, I mean the rectangular channel, and we already know the width of the channel, so this area is equal to width of the channel times the water depth, and this B is equal to 5 feet, as we write on here. Okay, so you can use the water depth to calculate the area, okay? Then, to calculate the velocity, we know the flow rate and we know the area, so the velocity simply can be calculated by the flow rate divided by the area, okay? And the flow rate here is 40 CFAs. Okay, so you just plug the area number into this equation, then you get this column for the velocity. After you know the velocity, you can calculate the specific force, specific energy using this equation. You know the velocity, you know the water depth, you know G is equal to 32.2 for the English unit, then you can calculate the specific energy. And similarly, we can use this equation for the specific force, because now you know this Q is equal to 8, the flow rate per unit width is equal to 8, and you know the velocity, which you just calculate in the third column here. Okay, and we know the specific weight for the water is equal to 62.4, and though for the water is equal to 1.94 pound per no. This is pound per cubic feet. Okay, so now you just need to plug in the different water depths for this y1 with corresponding velocity for this term. Then you can calculate the column for the specific force. After you finish this table, you can use the Excel to plot the curve. So we have the axis with the specific energy here, and we have the y-axis equal to the depth, water depth. And similarly, we can plot the specific force curve with the axis equal to the specific force, and the y-axis is the water depth. Okay. Now let's move on to the next question, which we want to classify this GVF, the gradually variate flow. And the slide, the question here, asks us to draw the critical flow and the normal depth in its figure first. Then we try to complete the water profile in this transaction channel. Okay, so let's do it. That's first, let me change the color first. Okay, so let's first draw the critical flow because critical depth, because critical depths will not change for the channel transition. So that's why we can plot the critical depths first and use it as the reference for our normal depth. Okay, so this red dashed line is the critical depth. Now we want to plot the normal depth. Change the color again. Okay, so because this is a steep slope, and for the steep slope, we have the normal depth that is lower than the critical depth. Because for the steep flow, we usually have the supercritical flow, which is have the water depth lower than its critical depth. Okay, so let's say this solid blue line is a normal depth for the first section. Okay, and because this transition is transit from the steeper channel to not steep channel, so that means the water depth for the normal water depth will be higher than the water depth that in the steeper channel, as I show on the screen here. That just gives the number of N2 and this is N1. Okay, and then we want to know what happened for this transaction part. Let me just erase more about it. And because this is a supercritical flow, so the supercritical flow will only affect, the water depth change is after the transaction point. It will have no backwater issue as the subcritical flow does. Okay, so that means if we draw the vertical line to separate this to point out this transaction area, this is a supercritical flow, so it will not affect for its upstream before this transaction area, but all the transition is happen after that. So we will have a curve start from here. Maybe let me change your color again. Okay, starting from here, slightly increase to the normal depth for the second section in this channel. Okay, and we can number this area. This is area 1, this is area 2, this is area 3. So this curve, this transition curve here, is denoted as S stand for the steep, and it's happened at the third area. So we give it number 3. So this curve here is denoted as S3 curve. Okay. Now let's move on to the next one. Here we will similarly follow this step, but I want to just show you in a larger plot here. Here, instead of the steeper channel to the steep channel, we have the channel from a milder channel to mild channel, which means the slope become steeper in this case, but it's still a mild channel. So let's follow the same step. Let's plot the critical depths out, because the critical depths will not change. Okay, so I will use this red dashed line. This is critical depth. And now I want to plot the normal depth. And again, this is a mild channel. That means it has subcritical flow, and subcritical flow have the definition that the normal depth is higher than the critical depth. So something here. And because the upstream channel is milder, so the normal depth should have a higher water level compared to this mild channel. So that just exaggerated a bit. We have something like this. So again, let's write this as yn1. This is as yn2. Okay. And let me plot this transition area out. Again, we want to decide how the flow transits in this transition area. And because this is a subcritical flow, so it will have a backwater issue, so the transition is happened before this black vertical line. And it is because it is the subcritical flow. So in this case, that just finish this line because this will not change for the downstream area. However, the transition is happened at here. Okay. And similarly, we can number these 3 areas with number 1, number 2, and number 3. Okay, so this curve is happened at the area 2, and it's a mild slope, so we can denote this curve as N2 curve. Okay, now let's move on to the next one. This time, we have the transition from the steep floor to a steeper channel. And we follow the exactly same procedure. In which we plot the critical depth out first. This is YC. And we want to plot the normal depth. So we have steep floor normal depth look like this, and because this becomes steeper, so the normal depth become lower. Okay, this is yn2, this is yn1, and we want to see how this water profile in this transition area look like. So let me okay, interesting. Let me erase these parts first. So again, this is a supercritical flow, so all the transition is happened after this transition point, which is this vertical black line. So to know that, we know they will have no effect at the upstream area, so it just remains the normal depth, and then the transition is happened at the downstream area. Okay, so again, assign the number for these three regions. And because this is a steep floor, a steep channel, so we have this curve denoted as S2 curve. All right. Now let's look at the last question we have for this recitation, for this homework. We have a sluice gate, look like this, and we have the horizontal water level for the upstream lake. We have another lake at the downstream. So we know the first thing we know that because this is a lake, so the water level here must be a subcritical flow. Okay, and you can consider this is as a mild slope because the slope is almost zero. It's zero because it's horizontal. And similarly, for the downstream, is also a mild and sub category. Okay, so again, we want to follow the same step. For example, we plot the critical flow, critical depth out. This is YC. And now we want to plot the normal depth. And because this flow is steep, right? Okay, it's steep. So the normal depth should be somewhere around here. And let me change the color for this one, okay? So let's say this is our normal depth. Actually, let me move this up a bit. Okay. Now let's plot the water profile. So for this transection area, the water will try to flow down to this normal depth. Okay. Then we occur a hydraulic jump because of this sluice gate. Okay. So we happen to have a this hydraulic jump and then gradually increase to a subcritical flow. Then for this region, again is the flow at this point is considered as the supercritical flow, and it will gradually increase to its normal depth. And then it will just stay at this normal depth. Then when you encounter this lake, then you will gradually fall down to the lake. Okay? So let me erase this for avoiding the confusion. So let's start to name the curve. Let me change the color. So we also have this area is 1, this area is 2, this area is 3, and this is a steep flow, so the curve here is named as S2 curve, and this is water hydraulic jump, and this increasing section is named as S1 curve because it's happened at the area 1. And similarly, here is area 1, area 2, area 3. So here from the supercritical to the normal depths, this curve is named as S3. Okay, and because this is a supercritical flow, so we don't consider, we don't name the curve down here. I mean, the water flow depth change will not affect any place before this line. Okay. So that is how we create this water profile for this question.